It's ironic and a little weird, but knowledge doesn't always bring understanding. For example, early people thought that the flat Earth rested on 3 whales standing on a huge turtle. With the advent of telescopes and, moreover, the science of astronomy, it became clear that we live on a geoid-shaped planet, but paradoxical as it sounds, a large amount of knowledge brings a large number of questions. If earlier lightning could be explained by the whim of god Zeus, now it has been proven that this is a physical phenomenon resulting from a large static charge in the atmosphere. And a whole series of new questions appears: what influences this phenomenon, how it happens, and others. It is the same with the universe that is around us. Scientists still do not know what it consists of, but develop various theories in this regard. One of the most widespread and interesting is the theory of dark matter. This is a special term for a substance that does not participate in electromagnetic influence. It is interesting that because of this, matter is not available for direct observation, which means that there is no direct evidence of its existence, but there are indirect factors indicating the presence of dark matter in space. Scientists have discovered this term in order to explain the problem of hidden mass in the effect of the abnormally high speed of rotation of the outer regions of galaxies. According to this theory, dark matter occupies about 25% of the entire universe, and when combined with dark energy, this figure reaches 95%. By comparison, ordinary matter, which we are used to seeing every day, takes up only about 5% of the mass. In other matters, these are not the only mysteries and amazing discoveries that dark matter holds. Features of dark matter. Dark matter is one of the most mysterious and at the same time the most common substances in the universe. Yes, scientists cannot see it, but they can study it. We can say that dark matter exists and even draw conclusions about some of its properties. By observing how it affects the matter and light that we can observe, especially in large-scale astrophysical environments. But the fact that dark matter has so far eluded direct laboratory detection means that a number of its properties remain an open question. So far, it is known that dark matter must be cold by nature. Theoretically, any hitherto undiscovered particle responsible for dark matter could have any mass. Moreover, it could be created moving fast, or slowly, or not at all, relative to the speed of light. But if dark matter moves fast, its properties will overwhelm the formation of structure on a small scale, resulting in structures different from what we can observe. In particular, we have 3 lines of observational evidence that limit the temperature of dark matter: gravitational lynchings of quasars, light absorption features of distant objects, and tidal energy flows in the vicinity of the Milky Way. All 3 indirect evidences speak of the same thing: dark matter must either be heavy enough or be born slow. In other words, dark matter must have been cold even in the earliest stages of the existence of the universe, not hot or warm. Dark matter is inert. According to scientists, it should not strongly interact with itself, with light, or with normal matter. There is no doubt that if dark matter exists, then in the young universe there must have been a way to create it. However, whatever the path, these interactions no longer occur and have not occurred in large numbers and for a very long time. Direct detection experiments have not revealed dark matter, which limits its possible mass and cross-section. It does not absorb or soar distant starlight, which means that this interaction is limited. They do not annihilate with themselves above a certain threshold, otherwise a large and diffuse gamma-ray signal would be visible in the center of galaxies. In fact, this corresponds 100% to the absence of interaction through any of the known mechanisms. If we hope to detect dark matter directly, we will have to push our limits of knowledge even further, and even then there is no guarantee that we will gain additional knowledge. In addition, dark matter effects dominate in small and smallest galaxies. This is a bit paradoxical, but it is confirmed by observations almost everywhere, wherever scientists pay attention. According to the laws of gravity, all forms of matter are treated equally, but other forces, such as nuclear and electromagnetic forces, act only on normal matter. When a big flash occurs in a galaxy and a new star is formed, All this radiation passes through dark matter, but can also collide with and be absorbed by normal matter. This means that if the total mass of the galaxy is small enough, this normal matter can be expelled by intense bursts of star formation. The smaller the galaxy, the more normal matter will be forced out, while all the dark matter will remain. The most striking examples, the dwarf galaxy Segway 1 and Segway 3, are the neighbors of the Milky Way. They contain only a few hundred stars, but have a total of about 600,000 solar masses. The ratio of dark matter to the mass of normal matter here is about 1,000 to 1, as opposed to 5 to 1 in most large-scale structures. Dark matter causes gravitational effects in places where there is no normal matter. This is one of the most compelling evidence that dark matter can't just be normal matter. When two groups or clusters of galaxies collide, the intergalactic gas and plasma collide and heat up, emitting X-rays, but the signal from the mass obtained from gravitational lensing shows that most of the mass is elsewhere. The main conclusion is that some new form of matter, dark matter, should make up most of the mass of the universe. Secrets of dark matter. Despite the presence of certain knowledge about dark matter, this substance has much more secrets, and no matter how hard scientists try, there is still a huge number of intriguing secrets. For example, we do not know which particles are responsible for dark matter, and even if they are particles at all. We only know that dark matter exists, that it does not interact with itself, normal matter, or radiation, and that it is cold. But we do not know what properties it actually has. Dark matter can be anything, because all our efforts to directly detect a particle or darker matter have led to nothing. We see its astrophysical effects indirectly, and this is obvious evidence, but real particles have not yet been detected. Dark matter can be either homogeneous or non-homogeneous, and this raises a number of interesting questions. For example, whether there are dark atoms, dark molecules, or even larger structures consisting entirely of dark matter. Perhaps there is a whole dark universe. Perhaps even including some kind of dark periodic table, consisting of several different types of dark particles that interact with each other, but according to their own physical laws. Conclusions. However, at the moment, scientists have already managed to obtain certain knowledge and systematize them. Dark matter is all around us. This is the name we have already given to the unknown mass in the universe, which remains invisible, and there is a lot of it. Research shows that about 70% of the universe is made up of dark energy. The other 25% is made up of a mysterious substance known as dark matter. We don't see it, we don't understand it, but we know it's out there somewhere. She is completely invisible. Dark matter is really hard to study because we don't have the ability to see it. This strange substance does not interact with light, so it is completely invisible. But how do we know that it exists? Everything is simple. Because dark matter indirectly affects the universe around us, creating gravitational and other anomalies. Dark matter binds galaxies together. Yes, dark matter cannot be seen, but it can be felt due to its powerful effect on the cosmos. Dark matter exerts a gravitational force, which means it pulls other matter towards itself, and yet there is so much of it that the gravitational force is enough to hold together entire galaxies, such as our Milky Way. This is why dark matter is often compared to a giant web that holds galaxies together in place. It distorts the appearance of space. We can also see the effects of dark matter just by looking at the sky. When astronomers observe distant galaxies, they often appear elongated and oddly shaped. This effect is known as gravitational lensing and is caused by the gravitational force of dark matter. This force is so great that it physically bends the light around the galaxy, distorting their appearance. Scientists have created maps of dark matter. Scientists have been able to put together maps of the cosmos, showing where they think dark matter is hiding. By studying the relic radiation left over from the Big Bang, scientists can identify areas in space where there is more radiation, and the more radiation, the more matter. In this way, we can identify hotspots where higher levels of dark matter can be concentrated. We don't know what dark matter is made of. Most scientists believe that dark matter is some kind of unique particle. We already know about photons, electrons, quarks, and many other particles, but there may be many others waiting to be discovered. One or more of these unidentified particles may be responsible for effects such as gravitational lensing and the web we associate with dark matter. Dark matter may not exist. It's funny, but dark matter may be an undiscovered particle or nothing at all. Some scientists believe that the effects we associate with dark matter are actually caused by gravity. Perhaps our existing theories of gravity are wrong and the effects we attribute to dark matter may be a quirk of gravity that we don't yet understand. Spaceships are hunting signs. So is dark matter a particle or a consequence of gravity? We don't know this yet. And more research is needed before any theory can be proven true or false. If dark matter particles exist, then they must collide with each other from time to time by an interaction that produces radiation, and so spacecraft have been equipped with advanced detectors to look for signs of this radiation. Some interesting results have emerged, but the search for hard evidence is still ongoing. In some countries, dark matter laboratories are hidden deep underground. If irrefutable evidence for the existence of dark matter is ever found, it will show up as very small effects. Interestingly, in order to detect their tiny signals, scientists have created dark matter laboratories deep underground, away from overwhelming background noise. For example, in the UK there is an underground laboratory, Bowlby. The dark matter laboratory in Severorkshire is located at a depth of more than 1,000 meters below the surface of the Earth. And other similar objects exist all over the world from Canada to Australia. We are getting closer to the truth about dark matter. There is still a lot we don't know when it comes to dark matter, and some mysteries may never be solved. But as technology advances, we are getting closer to the truth. Dark matter can be complex, elusive, and mysterious. But scientists around the world will continue to hunt, and what they discover could end up changing our very understanding of the cosmos. Subscribe to the channel. Make us happy.